Welcome to day 7. Your homework for tonight, you're going to be doing the answers algebraically, and then you also got a calendar problem. For the homework, we started out with some arc length ones. Remember, that's 2 pi, your radius, which is either your x part or your y part, depending if you're going over the x-axis or y-axis, and then your arc length. Arc length, remember, is square root of dx over dt squared plus dy over dt squared. So when you filled those in, we had the 4 minus 2t for the first one because we were going over the x-axis, so your radius would just be a y. And then the second one, we go over the y-axis, so our radius was the x, which was t. And both those neatened up pretty nice, and the antiderivatives hopefully weren't too bad. So then we get into the polar ones. These first few were like ones that we saw the other day, so graph it, do your trace, and then we want to see when we start tracing back over itself again. So 2 pi is where we would complete our cycle, and we wouldn't include the 2 pi because then it would be two values at the same spot. And the next one, if you had to kind of keep track as you were tracing through, but you got through everything after 4 pi. And for 45, in order to graph it, you had to get the r by itself, so we should have had a plus and minus. So in both instances, it was from 0 to pi over 2 to get through the cycle. So that first quadrant one was the positive loop, and the negative one was in the third quadrant. So we want to find, well, first off, we got our picture there. We're drawing in our tangent line at theta equals 0. Now we know it's there as opposed to off to the left, because when you put 0 in for theta, cos of theta, or cos of 0 is 1, so you get 3 minus 2, which is 1. If you had gotten, say, a negative radius, then it would be over on the left when theta is 0. So we've got written out there our r sine theta for y, our r cos theta. Do your product rule for both the y and the x parts. When you put in theta equals 0, anything that has a sign will be 0. So all the spots will be 0 except for the second term in the numerator, which will end up giving you 1. Well, 1 over 0 is undefined, and we see that kind of makes sense based on our tangent line that we drew. So graph that one on your calculator in 57. You've got your r sine theta. Since r was 3 sine theta, you could write y as just 3 sine squared. You got your r cos theta for x. Do your derivative of the y part, derivative of the x part. Top, you could just do a chain rule. Bottom, you had to do product rule. And then we're doing at pi over 3, which is 60 degrees. So you're using your 30, 60, 90 triangle. Sine of that is square root of 3 over 2. Cos is a half. When we fill each of those in, we can do a keep change flip at the end, and we should get negative radical 3. 58, your radius was just 4, so we had 4 sine theta, 4 cos theta. Derivative was pretty quick. We get a negative cotangent theta. At pi over 4, your adjacent over your opposite would be minus 1 over 1, so we just get negative 1. And that slope looks reasonable based on the tangent line we drew from the graph. So start out, write your r sine theta and r cos theta. Do your derivative by doing product rule for the y part on top, product rule for the x part on bottom. I chose to then neaten that up a little bit. Horizontal tangent lines when the slope is equal to 0, so that means we want our numerator equal to 0. You can pull out a cos theta there, set them each equal to 0. You get pi over 2, 3 pi over 2 for the cos 0. Then you get sine as a half, which gives you pi over 6 and 5 pi over 6. Well, if we look at our graph, here's where we are at 0. Here's pi over 2. Here's pi, 3 pi over 2, and then we get back to 2 pi or 0. So at pi over 2, there's a corner point there. So we have to reject that because there's actually not any slope. So our values where there's horizontal and vertical would just be the 3 pi over 2, the pi over 6, and the 5 pi over 6. Now, as I'm looking at this, it looks like it says we should have points. So I probably should have written those as points. So for the 3 pi over 2, sine of 3 pi over 2 would be -1, minus the -1 would make this be 2. When you do pi over 6, sine of pi over 6 is a half, 1 minus a half is a half. 5 pi over 6 is also a half because it's a 30-degree reference angle in the second quadrant. 1 minus a half is a half. So those are the actual points of horizontal tangency that we have. So that's that bottom one. That would be like here and like there or so, wherever that is on the graph. Now the vertical tangency, we want the slope to be undefined, so set the denominator equal to 0. I replace the cos squared with 1 minus sine squared theta, distribute the negative and combine like terms, then that will factor into 2 sine theta plus 1 and sine theta minus 1. So we end up with sine theta is a negative a half. So negative quadrants are 3 and 4. 30-degree reference angle would give us 7 pi over 6, 11 pi over 6. Sine theta equals 1 at pi over 2. And we know from before that we have to reject that. Well, our points now, because I forgot to write those, we'll have something comma 7 pi over 6, and we'll have something comma 11 pi over 6. So 7 pi over 6 in sine is going to be a 1/2, but those are both the negative quadrants. So 1 minus a negative 1/2 will give us 3/2. And then same thing for the other one. We'll have 1 minus a negative 1/2, so we'll get 3/2. So if we do our R and fill it into the Y and the X, we've got our derivative equation there. The horizontal is when the top is equal to 0. It's pretty messy, but you can pull out a 2a sine theta cos theta. So that's going to be 0 anytime sine or cos is 0. So all the n pi over 2's basically. And then cos squared theta minus sine squared theta, those would be equal. If you set that equal to 0, that's when sine squared is equal to cos squared. And if you took the square root there, that would be when one is equal to plus and minus the other. So that would be at all your 45-degree reference angles. So you got pi over 4, 3 pi over 4, 5 pi over 7 pi over 4. But our graph, if you graph that, and a you could just pick as some number, so you could just graph it as sine theta cos squared theta, repeats after pi. So we would want only the ones that go up through pi. So this one only wanted the horizontal points of tangency. So we just need to watch out for when they would be undefined. The denominator has a cos in every term. So anywhere that cos would be 0, we would get an undefined. So of the 0, the pi over 2, the pi over 4, and the 3 pi over 4, the pi over 2 is where cos is 0, so we'll reject that one, and only the 0, pi over 4, and 3 pi over 4 will find the points. Well, if we sub those into our R here, we'll get 0 for the radius, 0 for the angle. If we sub the pi over 4 in, it'll neaten up to square root of 2a over 4 for the radius and pi over 4 for the angle. And if you sub the 3 pi over 4 in, we get the same radius and just a 3 pi over 4 angle. So at the pole, we have a corner point, so there's no tangent line, even though when you set it equal to 0, if the value of theta you get is a corner point at the pole, there would be no tangent line. So pretty much same idea in 70, even though we got theta equals 0. When theta is equal to 0, there's a corner point at the tangent line, or a corner point at the pole. So for these ones, set your radius equal to 0 and solve. Notice we don't have any corner points we have to worry about here, because as this is going, it's really doing something like that. So it's smooth as it goes through. So we end up getting cos 3 theta is equal to 0. Well, we want 3 theta to equal the odd pi over 2's, because that's when cos is 0. So you get pi over 6, pi over 2, and 5 pi over 6. Now, as we saw in the yesterday's video, in polar form, that's just a line. So theta of pi over 6, well, that is where all the positive radii are, and there's all the negative radii. So a theta equals an angle is actually a line in polar form. So here, as we go through, if you trace this one, it goes here to here, and then because it goes down, you've got a vertical tangent line there. Then you've got a horizontal tangent line, then back to a vertical tangent line, and then back to a horizontal. So the vertical is happening at theta equals 0, or back when it gets to 2 pi, and the horizontal was pi over 2, and then the pi and the 3 pi over 2, that's the same equation of a line. And just to show you where that's coming from, let's look at the theta equals 0 and theta equals pi. Theta equals 0, here's theta equals 0 with positive radii, there's theta equals 0 with negative radii. If you do theta equals pi, here's theta equals pi with positive radii, theta equals pi with negative radii. So they end up being the same thing, so that's why we don't have to state them both. And then to match up your equations, I like to always just put 0 in for theta to help match them up. So when we put 0 in for theta, this one's going to get 0. 96, it'll be cos of 0, so that one's going to give you a radius of 4. Secant of 0, well, that's the reciprocal of cos, and cos of 0 is 1, so that one's going to give us 2. And this one's going to give us 2 times 3, which is 6. So 0 should be when you're going right on the x-axis, that's where 0 equals theta. Well, here's 0, comma 6. This one, there's nothing to the right, so that must be the 0, comma 0. Here's 0, comma 2, and there's 0, comma 4. So that's how you can differentiate between those three. So CB, AD. All right, today we are going to work with areas bound by polar curves. So we need to go back to geometry first. When you had an area of a sector, so think of it as the area of a slice of pizza or area of a slice of pie, you set up a proportion. You did your partial angle theta over all the way around, which would be 2 pi. Now, you might have in geometry looked at it in degrees and said 360, but we're in radians and calculus, so we'll put 2 pi there. And then you did your area of your sector, which was the small area, over the area of the whole circle, which is pi r squared. Well, we're going to solve this for capital A. So this would be theta over 2 pi times pi r squared is equal to A. So in other words, the pi's wipe out, and we're going to write this as 1/2 r squared times theta. So that's a direct formula that can give you the area of a sector in a circle. Well, suppose we want to find the area enclosed by this polar graph. When we had just regular functions and we wanted to find the area between the graph and the x-axis, we split it into rectangles to find that. Well, with a polar graph, everything is in relation to the pole. So if we go to the next page, we won't split this into rectangles. Think of it as you're slicing it like a pie. So you're starting at the pole and you're having slices come out from the pole to have that cut into like little wedges. Well, as we slice those, like where those blue arrows are pointing, those radii of the polar graph, they're not the same. Our angle of that slice, we're going to call delta theta, okay, the change in theta. But like we let the number of rectangles go to infinity when we did Riemann sums, and that made our delta x get infinitely small. If we have our number of wedges that we're doing go to infinity, that will make delta theta get infinitely small. As delta theta gets infinitely small, those two radii are going to approach the same length and be essentially the same. So when our number of wedges that we're doing goes to infinity, the area of our sector will approach our area formula we just did. 1/2 theta times r squared. Well, theta is our angle at the inside there, which is our delta theta. And our radius is always going to be some function of theta, and then we have the half. And then we would add those all up, and that's going to eventually become an integral as n goes to infinity, because those radii will approach each other then. So that's our basic setup that we are going to work with. So you can either think of the radius as some function of theta, or you can just think of it as being the r. So our general setup for finding the area bound by a polar curve is our integral from whatever value we start at. Now notice these are theta values. So alpha and beta here are values of theta. So whatever value of theta our curve starts at to whatever value of theta our curve ends at, and you do 1/2 your radius expression squared and then d theta. So we have this one here, and we want to find the area that is completely enclosed by it. Well, we need to see how long it takes to graph the whole thing. You could punch in your calculator and trace to see, but you can probably figure it out just by subbing in the nice values. Cos of 0 is 1, 1 plus 1 is 2, 2 times 3 is 6. So there's our 0. Pi over 2 for cos is 0, 0 plus 1 is 1, 1 times 3 is 3. So that's our pi over 2. So it seems like it's jumping by pi over 2 every time. Cos of pi is -1, so that gives us 0. So there's our pi 1. Cos of 3 pi over 2 is back to 0. And we get back 4. So 3 pi over 2, the angle is going down. So when it's a positive radius, it should go down. Okay, even though on like an xy, it's saying it's -4. Those are rectangular values we're seeing there. And then we would come back to 2 pi here. So we're going the integral from 0 to 2 pi, that tells us. We can put the 1/2 out here, and we would have our radius squared, and then we'll have d theta. Well, the 3 squared is going to give us 9, so I'm just going to throw a 9/2 out front. Oops, and I forgot my pi up on the top here. We need to add that in. So we're going to have 9/2 from 0 to 2 pi, and then we're going to have to FOIL out cos theta plus 1. Well, that'll give us cos squared theta plus 2 cos theta plus 1, and then we'll have our d theta. Well, we've got to recall something from Unit 6. We had our power reduction formulas. We had that cos squared theta was equal to 1/2 plus 1/2 cos 2 theta. And we had sine was the same thing but with a subtraction. 1/2 minus 1/2 cos 2 theta. And what that did is it reduced the power so that then we could take the antiderivative of it. So what we're going to have here, we'll have 9 halves, integral from 0 to 2 pi, but instead of cos squared theta, we're going to have 1 half plus 1 half cos 2 theta, and then the rest of the stuff will stay the same. And we'll just do a quick combining of like terms before we take our antiderivative. So that's going to be a half cos 2 theta plus 2 cos theta plus 3 halves. So we'll now do our antiderivative. So when we saw this in Unit 6, we saw that cos 2 theta, technically we have to do a u substitution. U would equal 2 theta, du would equal 2d theta, so we'd have to do a correction by a half. So whatever was inside there, when you do your antiderivative, you just got to multiply by 1 over it out front. So because of that, we're going to have 1/4 sine 2 theta plus 2 sine theta plus 3 halves theta. And we're going from 0 to 2 pi. Well, this is 9 halves. When we sub in 2 pi, we're going to get sine of 4 pi. Sine of 0 pi, 2 pi, 3 pi, 4 pi, they're all 0. Sine of 2 pi, again, is going to be 0. And 2 pi times 3 halves is going to give us 6 pi. Sorry, 3 pi. I take that back. I forgot that divided by 2. Minus, start a parenthesis, sine of 0 is 0. Sine of 0 is 0. 3 halves times 0 is 0. So this is just 3 pi times 9 halves. So we just get 27 pi over 2 is our area of that enclosed space. So if we move on to the next one, we've got a graph that has petals. So the strategy here is to find the area of just one petal and then go from there. Once we find the area of that one petal, we can just stick a 3 out in front, and that'll give us the area of the entire enclosed region. So we need to find what value of theta a petal starts at and what value of theta a petal ends at. Well, when the petals start and end, they have a radius of 0. So we can do 0 equals 3 cos of 3 theta. Well, that's 0 equals cos 3 theta. And cos is equal to 0 at all the odd pi over 2's. So we'll have pi over 2 equals 3 theta. We'll have 3 pi over 2 equals 3 theta. If we go the other direction, minus pi over 2 is equal to 3 theta. So theta would equal negative pi over 6. Theta would equal pi over 6. Theta would equal pi over 2. And we've got to see, where's this graph starting? If you put in 0 for theta, cos of theta is 1, and we get back 3. So that's our point at theta equals 0. So that means our petal is starting at our solutions here that are on either side of 0. So this one here, then going this way, that must be the negative pi over 6. And then it comes through here at theta equals 0, and then it finishes the petal at positive pi over 6. So we're going to do it as 3 times the integral of negative pi over 6 to pi over 6. Now alternatively, you could have said, oh, well, this pedal starts at pi over 6. And then it goes through and it finishes off at pi over 2. So you could have also done the integral from pi over 6 to pi over 2. You'll get the same answer. So we need our r squared. So we'll have 3 cos 3 theta squared and then d theta. And then out front we need our 1/2. So I'm just going to make this be 3 over 2. Well, if we square this, 3 squared is 9. So I'm going to put that out front and make it 27 over 2. And then we'll have cos squared of 3 theta d theta. In these problems, very common that you have to do power reduction because we're squaring and our radius often has sines and coses in them. So we'll have 27 over 2, integral negative pi over 6 to pi over 6. We will have 1/2 plus 1/2 cos. The inside doubles, so we have 6 theta and then d theta. So we're ready for our antiderivative. We'll have 27 over 2. We'll have 1/2 theta. We're going to have sine 6 theta now. Out front, we got to correct by a 6th, so we'll have 1/12. And we're going to evaluate that from negative pi over 6 to pi over 6. So this will be 27 over 2. Pi over 6 times 1/2 will give us pi over 12. Pi over 6 times 6 gives us pi. Sine of pi is 0. Minus, start a parenthesis. We'll get negative pi over 12 when we sub into the 1/2 theta. Negative pi over 6 times 6 is negative pi. All multiples, all integer multiples of pi are 0 for sine. Minus the minus will make this a plus. So we'll have 27 over 2 times 2 pi over 12, which is the same as pi over 6. And we'll end up with 27 pi over 12. We can reduce that, divide them both by 3, and you get 9 pi over 4. All right, one last one for today. So we want to find just the shaded area there of the limacon. We've got its radius equation given there. Our strategy is to find that shaded area. We're going to find the whole area, including that little loop that's missing, and then we'll subtract off the little loop. So we'll do an area from here to here, and then we'll subtract off our area from there to there. So that's the plan that we're going to work with. Well, to figure that out, we've got to find the values where the radius is 0. That'll tell us where it's passing through. So we're going to have 0 equals radical 2 minus 2 cos theta. Or in other words, that's 2 cos theta equals radical 2. Divide the 2 over, you got cos theta is radical 2 over 2. Well, cos is positive. So that's going to be in the first and the fourth quadrant. Radical 2 over 2 we get from a 45-degree reference angle. So we're working with a pi over 4 reference angle. So we would be working with pi over 4 when it's in the first quadrant and 7 pi over 4 when it's in the second quadrant. So let's go back to the graph here. And I think it's always helpful to sub in 0 and see where that point is going to be. When we sub in 0, cos of 0 is 1, so we'll get square root of 2 minus 2. Well, 2 is really square root of 4, so square root of 2 minus 2 is a negative number. So this is actually our point at 0, theta equals 0. So our part we want to subtract, that would be the places where the radius is 0 on either side of that. One would be negative, one would be positive. So for this loop here, we're going to do it from negative pi over 4 to pi over 4. Okay, because if we're getting in the fourth quadrant, you could also do that going backwards negative. Well, then after we get to the pi over 4, it's going to loop through to give us this part, and that'll finish at a pi over 4 reference angle in the fourth quadrant again, but this time we went in the positive direction, so this will be from pi over 4 to 7 pi over 4. So the strategy is to do our area with that radius from pi over 4 to 7 pi over 4. That'll give us the big one. And then subtract off our little loop there from negative pi over 4 to 4 pi over 4. Now, you could have done the little loop and done 7 pi over 4 to 9 pi over 4, and that would be the same thing. Okay, so we can fill in these blanks. The inner loop we said was negative pi over 4 to pi over 4. And then the outer loop was pi over 4 to 7 pi over 4. So we're going to do the outer loop minus the inner loop. So we're going to have 1/2 the integral pi over 4 to 7 pi over 4. We'll have our radius squared, so square root of 2 minus 2 cos theta squared d theta, minus now our inner loop area, which is 1/2 integral from minus pi over 4 to pi over 4 of that same thing. And because we have the same for both, I think it's advantageous to take it off to the side and work it out. So when we square that, square root of 2 times square root of 2 is 2. Our inners and outers are both going to give us a minus 2 square root of 2 cos. So that'll give us minus 4 square root of 2 cos theta. And then negative 2 cos theta times negative 2 cos theta will give us 4 cos squared theta. But then we're going to have to do a power reduction. So this will be 2 minus 4 square root of 2 cos theta plus 4 times 1/2 plus 1/2 cos 2 theta. If we distribute our 4, we'll get plus 2 cos 2 theta. And combine your like terms, we'll have 4 minus 4 square root of 2 cos theta plus 2 cos 2 theta. And that's our neatened up version of what's going to be in both those integrals. And then we don't have to worry about the doing it all twice. Now, what I'm going to do here is notice we have 1/2 in front of each of those. So what I'm going to do is I'm going to go through and distribute that 1/2, just so we don't have to worry about it. Everything was multiples of 2, so it should work out nice. So we're now going to have 2 minus 2 square root of 2 cos theta plus cos of 2 theta. And again, that's because I distributed the half through. And we'll have the same thing over here. I forgot my d theta on that one. So antiderivatives now, we should have 2 theta Cos's antiderivative is sine, so minus 2 square root of 2 sine theta. We got to do our correction with the cos 2 theta, so we'll have plus 1/2 sine of 2 theta. And that's going to go from pi over 4 to 7 pi over 4. Minus, we'll have the exact same thing over here. But we're going from negative pi over 4 to pi over 4. So if we fill in 7 pi over 4 times 2 gives us 7 pi over 2. Sine of 7 pi over 4, that's a 45-degree reference angle in the fourth quadrant. So that would be negative square root of 2 over 2. Negative square root of 2 over 2 times the negative will give us a positive. The 2 and the over 2 wipe out, and square root of 2 times square root of 2 will just give us 2. If we do 7 pi over 4 times 2, that gives us 14 pi over 4, which reduces to 7 pi over 2. Here's 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. So it's at the same spot as 270, and sine is negative 1 at 270, so we get a negative 1/2. Minus, start a parenthesis, pi over 4 times 2 will give us pi over 2. Sine of pi over 4 is either square root of 2 over 2 or 1 over square root of 2, so we get negative 2. Pi over 4 times 2 is pi over 2. Sine of pi over 2 is 1, so we get plus 1/2. Minus, now notice we're subbing pi over 4 into start, which is what we just subbed in. So we can just copy those ones over. That saves us a little bit of brain power. Minus, start a parenthesis. Negative pi over 4 times 2 will give us negative pi over 2. Negative pi over 4 in the for sine is going to be a negative 1 over square root of 2. So it'll give us a positive 2. And then negative pi over 4 times 2 is negative pi over 2, which is the same as 270. Sine is negative 1 there, so we'll get negative 1/2. So I'm going to go through and distribute negatives. So this will be plus, minus, plus, minus. I'll distribute this negative first, so it'll be plus. That'll become a minus, a plus, a minus, and a plus, and that'll apply to all those then. So let's do our pi over 2's. We have 7 pi over 2 minus pi over 2. That gives us 6 pi over 2. Minus pi over 2 gives us 5 pi over 2. Minus pi over 2 gives us 4 pi over 2. So 4 pi over 2 gives us 2 pi. Let's do our integers. We have 2 plus 2 is 4, plus 2 is 8. Sorry, plus 2 is 6, plus 2 is 8. We got a plus 8 from the integers. Now let's do our fractions. We have 1, 2, 3, 4, negative 1/2, so that's negative 2. So this will end up giving us 2 pi plus 6. And that's the area of our shaded region. We did the big loop minus the little loop that we didn't want. That's it for this video. Sorry it was a long one. Have a great rest of your day.